This is Group 21's project for the Maths Experience by Aina Brennan, Nevin Buckley, James Griffin and Michael McMahon. Our two questions are: find the values of x at which the function g of x equals 4x cubed plus 13x squared plus 14x minus 19 and that it has stationary points. Our second question is: find all the stationary points for the function f of x equals 3x squared plus 21x minus 77 and determine whether they are local max, local minimum or saddle points. Tackling question 1. Find all the values of x at which the cubed plus 13x squared plus 14x minus 19 and it has stationary points. To complete this question, we must understand that stationary points are the point or points on a graph where the slope of the graph is equal to 0, for example at a local max or a local minimum. From the graph we can see the local max and minimum points highlighted in green. The red line is when the slope is positive, i.e. greater than 0, and the blue line is when the slope is negative, i.e. less than 0. When we differentiate a function once, we get what is called the first derivative. This new function can be used to find the rate at which the function changes for different values of x, i.e. the slope. We know that stationary points have a slope of 0, so we let our first derivative equal 0. Differentiate the function, let the first derivative equal 0 and solve for x. Our first question: g of x is equal to 4x cubed plus 13x squared plus 14x minus 19. When differentiating a function we must remember that g of x is equal to x to the power of n. We multiply down by the power and subtract 1 from the power. G dash x, the first derivative, is equal to nx to n minus 1. Question 1. G of x equals 4x cubed plus 13x squared plus 14x minus 19. G dash x is equal to 3 by 4x to the power of 3 minus 1 plus 2 by 13x to the power of 2 minus 1 plus 1 by 14x to the power of 1 minus 1. G dash x is equal to 12x squared plus 26x to the power of 1 plus 14x to the power of 0. Remember, anything to the power of 0 is equal to 1. So we get g dash x equal to 12x squared plus 26x to the power of 1 plus 14 by 1. So g dash x equals 12x squared plus 26x to the power of 1 plus 14. We now let the function g dash x equals 0 and solve for x. Remember in the last slide we found g dash x equal to 12x squared plus 26x to the power of 1 plus 14. Let g dash x equal 12x squared plus 26x to the power of 1 plus 14 equal to 0. We can now treat this as a normal quadratic equation and attempt to factorize and solve for x. The factors of g dash x cannot be written as integers, so we must use the following formula: minus b plus or minus the square root of b squared minus 4ac all over 2a. G dash x equals 12x squared plus 26x plus 14. We now label our a, b and c. A is equal to 12, b is equal to 26 and c is equal to 14. We now fit these values into our formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. Our a value is equal to 12, b is equal to 26 and c is equal to 14. We now sub in these values and we get minus 26 plus or minus the square root of 26 squared minus 4 by 12 by 14 all divided by 2 by 12. When we sub in these values we get minus 26 plus or minus the square root of 676 minus 672 all divided by 24. This now splits into minus 26 plus the square root of 676 minus 672 divided by 24, or minus 26 minus the square root of 676 minus 672 all over 24. This then gives us minus 26 plus the square root of 4 divided by 24, or minus 26 minus the square root of 4 divided by 24. We then get minus 26 plus 2 divided by 24, or minus 26 minus 2 divided by 24. This then gives us minus 24 divided by 24, or minus 28 divided by 24. So x is equal to minus 1, or x is equal to minus 7 over 6. Question 2. Find all the stationary points for the function f of x equals 3x squared plus 21x minus 77 and determine whether they are a local max, local minimum, or a saddle point. We will approach this question in the same way as question 1, however we will need to differentiate twice to check the nature of our saddle point. Question 2. When we differentiate our first derivative, naturally enough we get a function that is called our second derivative. This tells us how quickly or slowly our slope is changing and informs us what shape our graph takes. Question 2. Find the stationary points by letting our first derivative f-x equal to 0 and solving for x. Find f"x, the second derivative. We can now sub in our value for x from the previous step. If f"x is greater than 0, it is a local minimum point. If f"x is less than 0, it is at a local maximum point. If f"x is equal to 0, it's at a saddle point. First, we write down our equation. F of x is equal to 3x squared plus 21x minus 77. Our first derivative, f-x, is then equal to 2 by 3x to the power of 2 minus 1 plus 1 by 21x to the power of 1 minus 1. Then we get f-x is equal to 6x plus 21x to the power of 0. Remember, when x is to the power of 0, it is equal to 1. So our first derivative, f-x, is equal to 6x plus 21. We'll now let our first derivative equal to 0. So 6x plus 21 is equal to 0. We then take 21 from both sides to get 6x on its own. So we get 6x plus 21 minus 21 is equal to minus 21. The plus 21 and minus 21 cancel, giving us 6x is equal to minus 21. We then divide both sides by 6, giving us 6 divided by 6 by x is equal to minus 21 divided by 6. This then gives us x is equal to minus 3.5. We have a stationary point at x is equal to minus 3.5. We must determine its nature by getting the second derivative and letting it equal to 0. Our first derivative, f-x, is equal to 6x plus 21. Our second derivative, f"x, is equal to 6. Remember, if the second derivative is greater than 0, it is at a local minimum. f"x is equal to 6. Therefore, it's greater than 0. The stationary point then, at minus 3.5, is at a local minimum. Thank you for watching.